Welcome everyone to the hands-on session. Okay, so Matteo and myself, we will take care of it. I start, and then Matteo continue later on. So please open Quantum Mobile, keep it ready for the hands-on. And also, these are the slides. You can find these slides in day 2. Yes, here it's called day2_hands-on.pdf. Okay, so yeah, we have 3 hours in total, and we have 1 hour for lunch in between. So we have really lots of time, and let's try to use it as effectively as possible. Okay, and this is the first exercise, calculation of the projected density of states of cobalt oxide with and without the Hubbard correction. This is the input file for cobalt oxide. So you're already familiar with the input file for the pw.x calculation in Quantum Espresso, so I don't want to spend too much time on it. Just very key points I would like to highlight. So this is the SCF calculation. So we say calculation equal SCF. Here we set up the structure, eyebrow 0, and the lattice parameter 8 Bohr. So since we use eyebrow 0, it means we also need to set up the cell parameters below in lat units, in units of the lattice parameter. And this is the cell parameters which were already optimized using the PBSol functional. For cobalt oxide, we have 4 atoms, 2 cobalt atoms and 2 oxygen atoms. That's why in the atomic positions we see cobalt 1 and cobalt 2 and 2 oxygens. We have cobalt 1 and cobalt 2, 2 types of oxygen, of cobalt, because this system is spin polarized. So we have 2 sublattices. So cobalt 1 corresponds to the spin up, and cobalt 2 corresponds to spin down. So that's why we use n spin equals to 2 to tell to the code that this is spin polarized calculation. And we set up starting magnetization for the first type, some value in the range from 0 to 1, let's say 0.5. And for the second cobalt, starting magnetization minus 0.5, something between 0 and -1. So just to tell to the code that first cobalt has initial magnetization up, and the second cobalt has initial magnetization down, as we want, because it's antiferromagnetic material. And then also we set occupations equal to smearing, because we actually already know that at the PBSol level, cobalt oxide is metallic. However, experimentally it is insulating. So since this is the PBSol calculation, we use smearing here. Convergence threshold is set to some reasonable value, 10 to the power minus 10. And pseudo potentials are also set here. They were generated using the PBSol function. So this is very basic. A brief reminder that to prepare this kind of inputs, you can use Quantum Espresso input generator. That is a very useful tool. You can find it using the link below. And pseudo potentials were taken from the SSP pseudo potential library that can be also found in the materials cloud here. So we don't need to think which pseudo potentials to use. We simply go to this website and pick up the most accurate pseudo potentials, which were tested against the all-electron calculations. So on the left, we see the recap of the SCF calculation. And on the right, we have a similar input file, but for the NSCF calculation, which means non-cell consistent field calculation. There are a few differences between the 2 inputs. First, we say calculation SCF or NSCF. And second, in the NSCF input, we need to set the number of bands, the parameter NB and D equals to 40. This is so because we want to compute the projected density of states. So we want to have not only the occupied states, but only a few empty states. So why the value of 40? It depends on the system, because we already checked before that you can see from the output of the SCF calculation what is the number of occupied states. Then you simply add a few more states to have a few empty states. So I will show you in a moment what does it mean. And for the k-points, for the SCF, we used the 3x3x3 k-point mesh. For the NSCF, denser k-mesh, 6x6x6. So why is it so? Because in SCF, we can use scarcer mesh because we simply need to converge the density. While in NSCF, we need to use denser k-mesh because we want to have very accurate projected density of states. If you want, you can use equal k-point meshes like 666 in both cases. It will just make your SCF calculation more expensive, but you will not really gain much. So that's why it's sometimes useful to use SCF with scarcer k-mesh and NSCF with denser k-mesh. But be careful, those are not well converged k-meshes. This is just for the demonstration purposes. They are very scarce, but in general, you need to converge both k-meshes. Once these two calculations are done, and we will do it in a moment. After that, the third calculation is the projected density of states calculation using the program project wave functions, proj_wfc. The input is here, it's pretty simple. The prefix and output directory is exactly the same as in the previous two inputs you see, prefix and out directory. Then we need to specify a few other keywords like Gauss. This is tell to the code that this is Gaussian broadening, the value of the broadening, the Gauss in Rydberg, the energy window for the PDOS, and the step delta E. And then I already prepared to you the GNU plot script called plot_PDOS.gp, where is all ready. You just need to run this GNU plot script to produce the final image. So this is the steps, and let's do it now. So we go now to Quantum Mobile, to day 2. In day 2, we go to exercise 1. Here we see readme.md. If you type cat readme, you see all these steps, and let's do them one by one. First, the self-consistent field calculation.
Iurii, sorry to interrupt.
Yes.
There's probably a mistake in the fact that NSCF and SCF inputs have different cell parameters from one another.
Okay.
Also in the slides.
Oh yes.
And some attendees are realizing that, and I was looking at that also.
Oh, okay. Okay. Thank you.
So maybe
yes.
we in the hands-on tutorial we just fix that.
Yes. Thank you. Yeah, it's a mistake. Sorry. Yes, indeed. Thank you. Yes, so we need to change cell parameters in the NSCF calculation here. Okay, so now we are running SCF. Let's open the output file because I would like that we see some useful information here. So if we go at the bottom of this output file, we see as usual total energy, Fermi energy, total magnetization is 0 as it should be because it's antiferromagnet. But also I would like to show you the output. Oh no, there is nothing here. So okay, I'll show you later. So this is standard DFT calculation. Now we need to modify a little bit the NSCF. So let's first open the SCF input file, copy cell parameters. It's actually, I did it on purpose so that you learn a little bit how to modify the input. No, just kidding. And here we remove the old cell parameters. Okay, we paste exactly the same as the SCF. Okay, we save. Okay, now, yeah, I can actually answer the question why we have 40 bands here. So to answer that, we open the previous output file, cobalt oxide SCF output. And at the top of this page, we go to the summary of the calculation. And here you will see number of constrained states 28. So this is the number of occupied states. So it's 28. I want to have a few more empty states. So I decided to take 12. You can take whatever number you like. Typically, I mean, we need to converge the PDOS up to some certain energy. So if you go to higher energy, you need to have more empty states. So here we say just for demonstration purpose and 12 states. So that's why it is 40. But it can be 30, it can be 50, whatever you decide. Now we run the NSCF calculation. Cobalt oxide.nscf.in and output cobalt oxide nscf.out, and we press enter. Okay, you see we have 64 K points, and the code runs one by one sequentially. So it takes a little bit of time. While waiting, maybe we can take some questions. So how is starting magnetization decided? Starting magnetization, yes, it's any value in the range from 0 to +1 and from 0 to -1. So any value. So in principle, the final result should not depend on this value, but in some exotic systems, it might result if you have many local minima. So if you set up different starting magnetization, your calculation can converge to different local minima. But if your system is pretty simple and it don't have complex potential energy surface, you choose just some fractional value between 0 +1 and 0 -1, and it should not matter really which exact value you take. Okay, the calculation took 1 minute 13 seconds. Okay, next step is to run the projected density of states calculation using the program proj.wfc. So we read the input, cobalt oxide.proj.wfc.in, and we write the output, cobalt oxide proj.wfc.out. So this is the PDOS calculation. It's fast. Yes, it took just 3 seconds. And finally, so you see this calculation produced many files here. So each file corresponds to the projection of the quantum wave functions on certain atomic orbitals. For example, for cobalt-1, we have 5 files, because in the pseudo potential we have 5 atomic orbitals. So they're labeled 1, 2, 3, 4, 5. And here you see the character of those orbitals, S, P, D, S, P. We are interested in the d orbitals, so that's why we will only plot the information from this file for the 3d orbitals of cobalt-1. And same for cobalt-2, we will take information from this file, cobalt-2 3d orbitals. And for oxygen, we take 2p orbitals. So if you are familiar with GNU-plot scripts, so the script is plot PDOS. So we already prepare everything here, but you can find here that we use information from those files that I just commented about. So for cobalt-1 and cobalt-2 3D states, and for oxygen 2p states. So we plot 3 graphs on the same plot. So we simply type GNU-plot and the name of the script, plot_pdos.gp. It takes 1 second and produces the file called cobalt oxide_pdos. We open it with the program called evins, cobalt oxide_pdos.eps, and this is our final result. So here we see on the y-axis projected density of states, On the x-axis, we have energy in electron volts. This energy was shifted by the value of the Fermi level. So this energy of the Fermi level was taken from the output of the SCF calculation. And we see in red cobalt 3D states for the majority spin. This is cobalt 1. And then in the green, we show cobalt 3D minority states. This is cobalt 2. And we see in blue oxygen 2p states. So you should also obtain exactly the same figure. If you have any problems, please tell us on Slack. So now I come back to the presentation. If I go too fast, please tell me. I slow down a little bit. Okay, so this is the result that we just obtained. So what we find is that DFT predicts cobalt to be metallic, which is obviously wrong because experimentally it is known to be insulating. So we want to see some band gap, but we don't see it. This is because we use PB-Sol. We know there are self-interaction errors. 3D states are over delocalized, and we see the calculation gives completely wrong prediction. And +U comes to the rescue. Let's try to use DFT+U and see if we manage to open the band gap. Now what we do is take in our original input files and we need to modify them slightly. All stays exactly the same as before. We just need to add a new card, which is called Hubbard card, which is shown at the bottom. Let me zoom in and explain in more detail each information in this card. So here it is. So first, the name of the card, which is Hubbard, written in capital letters. Then in brackets, we write the type of Hubbard projector functions that we just explained in the lecture. You can have atomic, orthoatomic. It's the most frequently used ones. Here we use orthoatomic. Then we say the letter of the Hubbard parameter, it's U, or it can be V. In this case, it's U. Then we say to which chemical elements we want to apply the Hubbard U correction. In our case, it's cobalt 1 and cobalt 2. And then we say which states of these chemical elements we want to correct with Hubbard U, because both cobalts, cobalt 1 and cobalt 2, they have 5 atomic orbitals. 3D, 3p, 3s, etc. So in principle, we can apply Hubbard correction to any of those. But in our case, we want to correct only 3D states. So that's why we write cobalt 1/3D, cobalt 2/3D. And finally, we put the value of the Hubbard U parameter. In this case, it's 6.3 and 6.3. It is exactly the same for 2 cobalt atoms, because these 2 cobalt atoms only differ by spin. But apart from that, the value of the Hubbard U is the same. Now, why this value of Hubbard U? Here, we just want to show you how it does it work. But later on, we will show you how to compute it. So suppose we already know how to compute it, we did it. Now we just plug in here the value, which is 6.3 in our case. And then we want to see if it opens the band gap or not. But later I will show you how to compute it. So yes, and the same for the NSCF input file. We need to add the Hubbard card and keep in mind that we need to fix the problem for cell parameters. The input file for the PDOS calculation does not change, it stays exactly the same. And the script for GNU plot also stays the same. I think we just need to change the Fermi energy, but if we don't, we need to change the Fermi energy. So let's do that. So the value is 6.3, let's remember this. So here we can clean this repository. We can remove these output files. You can write but be careful, don't remove too much. rm_.out. So we remove those. Then we remove PDOS output files. It's not strictly necessary to remove it. They will be overwritten if you don't remove them, but I just prefer to remove them. Have a clean repository. And we can also remove the temporary directory. So rm minus rf and tmp. Okay, so we have clean repository. Now we can modify the input files. So here we go at the bottom of this input file, and we need to type Hubbard card. The type of Hubbard projector is orthoatomic. And then we need to specify that we apply Hubbard U to cobalt 1/3D states. And the value of U6.3. Okay. And same for the second cobalt. So we just type cobalt, change cobalt 1 to cobalt 2. That's it. So this we copy and paste also in the NSCF input. This we close and save. Column WQ. Now we open the NSCF output. Go at the bottom and paste the Hubbard card that we just typed in the NSCF in the SCF input. Okay, that's the only modification. Now we need to repeat the same steps as before. pw.x, read the input from cobalt oxide scf.input, and write output scf.out. Press enter. Calculation is running. So there is a question, particular reason for choosing MV smearing. So MV smearing is the Marzari-Vanderbilt, or also known as cold smearing. This is the most accurate type of smearing. Another popular one is Methfessel-Paxton, but that has some issues because it can allow negative occupancies, which doesn't make any physical sense. So Marzari-Vanderbilt is more accurate. That's why we strongly recommend to use it. So what would happen if the starting magnetization is set by error to a value more than 1.0 or less than -1.0? It will simply stop. The code does not allow it. Okay, the SCF is finished. Now we need to do NSCF. pw.x, we read the input for NSCF and write the output in NSCF.out. Again, it takes some time. So while waiting for this, we can inspect the output file of the SCF calculation. So I open a second terminal. Okay, now let's open the output file SCF calculation. Go at the bottom. So we can see that total magnetization is still 0, so it's still antiferromagnet as it should be. We have the Fermi energy written here. But also now in the output we have extra information here. Let me just go to the last occurrence of this. So in the output file we see since we are running DFT+U calculation, the code prints some extra information. In particular, the information about Hubbard occupations. So we have two Hubbard atoms, cobalt 1 and cobalt 2. That's why we have information for atom 1 and below for atom 2. What is reported here is the trace of the occupation. So occupation matrix called NS, and this is the trace. So this tells us how many electrons are sitting in the 3D shell of cobalt. So we have upspin component, which is 4.96, downspin component, which is 2.28, and the total, which is the sum of the two, which is 7.25. Also, the code reports the atomic magnetic moment, which is 2.68 magneton Bohr. And then for each spin, it reports more information. So we have for spin 1, this block, and for spin 2, the second block. So for spin 1, we have the original occupation matrix before the diagonalization. It's here. So it is 5 by 5 matrix because we are dealing with 3D electrons. So that's why we have the dimension 5 by 5. Because the orbital quantum number is 2, so we can have 5 values from minus L to plus L. And we can see that we have on the diagonal some values. And if we take the sum of those values, we obtain this number, 4.96. But you can notice that there are also some very small off-diagonal values. In this case, they're really negligible, but in other cases, it can be very significant. And when we diagonalize this matrix, we obtain the eigenvalues reported here and the corresponding eigenvectors. And the same we have for spin 2. So we see that spin up channel is occupied because all eigenvalues are close to 1, while the spin down channel is, so the 3 eigenvalues are essentially empty, while the other 2 are occupied. If you do the same analysis for the second cobalt, you will see that it is reversed, but because the spin is opposite. So we have that for the spin 1, the first 3 empty and the last 2 are occupied, while for the second spin, all is occupied. So it's really mirrored. So this information is extremely useful. Whenever you use DFT+U, it's always very useful to check this information. Okay, so the NSCF calculation is finished. Now we do the third step, which is the PDOS calculation. So we type proj wfc.x, read the information from the input, and write the results in the output. This takes just a few seconds. And the final step is to run the GNU plot script. But since we applied the +U correction, the Fermi energy has changed. So we should modify it in the script. So we go back to the SCF input. Sorry, it's already opened. So the value of the Fermi energy is 15.62. 15.62. Let's put it in the script. Okay, here it is. Here we have this shift, 15.62. So 3 lines to modify. All the rest stays the same. We save it. And now we can run the GNU plot script. This produced the file cobalt oxide pdos.eps, and we can visualize it with Levin's problem. And this is the result. We are very happy because thanks to the +U correction, there is a band gap that was opened. So now we can go back to the slides. Yeah, so there is a band gap opened, which is very good because this is in agreement with experiments, because experimentally there is a band gap. So now let's recap again. In DFT, we didn't have a gap, we had a metal. By applying +U, we opened the gap. The experimental value of the band gap is 2.5 plus minus 0.3 eV. And with DFT+U, we predict 2.6, which falls in the experimental uncertainty, which is very good. So, of course, this band gap depends a lot on the value of the Hubbard U parameter. So in this case, we used 6.3 because I performed self-consistent calculation of the Hubbard U and I obtained that it is 6.3. And as you can see, with this ab initio value of the Hubbard U parameter, we predict the band gap, which is very good, in very good agreement with experiments. Not always we have this such a good band gap, but in this case, it is very good. And we will compute this value of the Hubbard U in the afternoon. So how are we doing in terms of time? We have still half an hour. Okay, this is great because we can do now together the second exercise for iron oxide. And then Matteo will continue with exercise 3 and exercise 4, either during this half an hour or after the lunch break. So, okay, now let's move to exercise 2. Any questions so far that were not answered on Slack? So there is one last which was not answered yet. DFT+U produce band gap of cobalt oxide. Should we use occupations fixed? Well, here, since we are running magnetic calculation, spin polarized calculation, we're obliged to use occupation smearing because we need to allow to the code to use fractional occupations. So if you put occupations fixed and try to use starting magnetization, the code will stop. You say you can't, you need to use smearing. So that's the answer. So it's a technical reason why we need to use smearing, because we use spin polarized calculation. We perform spin polarized calculation. Okay, let's move on. So nicely, we saw that for cobalt oxide, +U opens a gap without any issues straightforwardly. But you will see now that in iron oxide, it's more tricky. So let's see what's happening. So this is the input file for iron oxide. It is essentially exactly the same as for cobalt oxide. I just re-optimized it at the PBSO level, so cell parameters are somewhat different. Here they coincide because I didn't do a mistake here. So we just, again, perform standard DFT calculation. So we already know the procedure. I would like to say that before, when we performed DFT calculation, there was no Hubbard card. But here we put it with some vanishing Hubbard U parameter. So we do so just because we want the code to print in the output the information about the Hubbard occupations, because we want to do some analysis. But in principle, we don't really need this Hubbard card when we want standard DFT calculation. And the following steps, PDOS calculation and script, are the same as before. So yes, we do these steps. Let's do them. Now we go to exercise 2. So we go to exercise 2. We already discussed the input files. Let's just check that all is as expected. Here actually I removed the Hubbard card, so we need to add it. Let's edit Hubbard orthotomic U iron 1 3D states 0.0001. And same for the second iron. Okay. And exactly the same Hubbard card we need to add to the NSCF calculation over here. Okay, so now we are ready to run all the 5 steps. So first, the ground state calculation. Okay, this is now standard DFT calculation, or if you want DFT+U with vanishing Hubbard-U parameter, which is essentially standard DFT. But you see the code outprints information about Hubbard occupations, which we want to know what is the occupations in a DFT case. Okay, takes some time. About 20 seconds, I think. Okay, the SCF has finished. Now we can run the NSCF calculation. This takes a bit more of time. So we should obtain again the metallic solution as shown here. Any questions on Slack? I see all was answered. Okay, so let's wait for this calculation to finish. So we should obtain this result, metallic solution, as in the case of cobalt oxide, which is obviously wrong. So next, what we want to try is in case of cobalt oxide, we want to apply some Hubbard-U correction. In this case, we choose the value of, well, we not choose, we actually computed from first principles. I did it. So consistently, and I obtained the value of 5.36. In the case of cobalt oxide, it was 6.3. So you see the value of the Hubbard-U depends on the chemical element, on the environment, and many factors. So we do SCF and NSCF with the Hubbard-U correction. And what we should find that there is no band gap. It is still metallic. So for some reason, in the case of cobalt oxide, it was enough just to apply Hubbard-U, it opens the gap. But here, surprisingly, we applied Hubbard-U and there is no band gap opening. So what is the problem? So let's first finish these calculations just to be sure that this is indeed the case. So this is the standard DFT, which is being finished soon. Okay, the next step is PDOS calculation. It's fast. Then again, we check the value of the Fermi energy because we need to make sure that in the script it is correct. So we open the SCF output and check the Fermi energy. Is 16.11. So we open the GNU plot script. 16.11. That's correct. So we can run this script without any modification. So we type GNU plot, the name of the script, plot underscore PDOS. This produces the EPS file. Well, it was not VI, but there is. Okay, with DFT, we obtain metallic solution as expected. That's fine. Now we want to run the standard DFT+U calculation. So let me keep these files. Let me create a directory DFT and move there, copy these files there. So I don't want to lose them. Okay. Now I can clean this repository. All right, and one more. Yes. Okay, now we want to run DFT+. Let's input the Hubbard U values in the input. So first is CF. We put here the value of 5.36 for both iron types, and the same for the NSCF, 5.36. Okay, now let's repeat all steps again. Okay, take some time. So the question, sorry, why you have to use the Fermi level of the SCF instead of the NSCF calculation? So actually yesterday there was a similar question and I answered to it. So the Fermi energy of SCF and NSCF, they should coincide. If you use dense enough K-point mesh, in both cases, they will coincide. If they don't coincide, it means some of them is not converged. In this case, the one of SCF, because the K mesh is scarce. But if you use dense enough K mesh, both Fermi energies should coincide. So it doesn't really matter if you take it from SCF or NCF, because it is the same. In this case, they don't, because it's not converged, because we don't have time to run very expensive calculations. But for demonstration purposes, it's enough. It's not really a big deal if it's not converged. It's already sufficient for us to discuss what we want to discuss. But for when you want to publish results, you need really to perform careful convergence tests.
Sorry, Iurii, there was someone who was asking to showing the Hubbard correction value again for FE. It was too quick, and yeah.
You mean 5.36?
Yeah, I think so.
Okay.
Yeah.
It's on the slides, by the way. So the slides are provided with the hands-on, so all this information should be available to everyone. But yes, please. 5.36 in the case of iron. It's a self-consistent value, which was also computed by us. Okay, so consistent calculation is still running. Almost there. So we have 15 minutes left, so we will finish this exercise and go for a break. So now we do the NSCF calculation. So as we know, this takes a bit more time. Let's be patient. Meanwhile, let's answer some questions. So which type of Hubbard projector was used in the older versions of Quantum Espresso, like 6.1, 6.5? As far as I remember, it was not possible to specify the Hubbard projector in older versions. So before, in the older versions and in the current latest version, the default is atomic, which means non-orthogonalized atomic orbitals. Now we really are obliged to specify explicitly in the input which type of Hubbard projectors you used. Before, if you don't specify, it's fine. You just use the default, which is atomic. But now we want that people really realize actually what do they use. Before it was like assumed silently that you use atomic, and people didn't really pay much attention to this. But now people are obliged to pay attention to this. You need really to write the input atomic or orthoatomic. And in the older versions, you still could choose. There was a parameter called U projection type. It was atomic or orthoatomic. As I say, it was not mandatory to specify it always, because if you don't specify anything, it was the default value, which was atomic. But now this doesn't work. There is no default. You really need to specify it. So could you please tell me, there is someone answering. Okay, maybe I'll let people answer in Slack. So the non-U DFT+U you obtained in the run was slightly different than the one in the day2 PDF file. Mix around the Fermi energy. Is this just because of change in settings? Yes, probably there is some slight mismatch. Yes, and maybe when I was preparing slides, what I put on slides and what I put here slightly mismatch. Apologies. But I don't expect there should be some very, very big differences. Okay, NSCF is finished. Now, let's run the PDOS calculation. This is fast. And okay, now before we run the GNU plot, let's check again the Fermi energy. It's 16.67. 16.67. We put it here. So we shift the PDOS by this energy. Now we are ready to run the GNU plot script. And we can visualize the PDOS. Okay, so this is the metallic solution. Let's check the slides. Yeah, more or less the same. So yes, we see that simply applying +U blindly does not open the gap. So what's the problem and what to do? And this we answer in the remaining 10 to 15 minutes. So the problem is that in iron oxide, unfortunately, we converge to the local minimum. And this local minimum is metallic. But instead, we want to converge to the global minimum, which is insulating. So essentially, the code didn't manage automatically to converge directly to the global minimum. It got stuck in some local minimum. This can happen, and this is one of those unfortunate cases. So what to do in this case? We need to do some trick, if we can say it like that. So we need to inspect the output file and check the Hubbard occupations and try to understand what's happening. So this is a screenshot of the output file of the DFT+U calculation. So as I said, atom 1 is iron 1 in red, and atom 2 is iron 2 in green. So we see the spin up, spin 1 or spin up for first iron is fully occupied channel. You see eigenvalues are almost all equal to 1. But for the second spin 2 or down spin channel, it's partially occupied. You see the first two are degenerate eigenvalues, are 0.075. Then we have another two degenerate values equal 0.253. And the last one, which is non-degenerate, which is 0.285. For the second atom, it's exactly the same, but mirrored. with respect to the spin channels. So I highlight here in blue circles these eigenvalues. They are the only ones that are not degenerate. And what we want to do now is to try to suggest to the code to fully occupy them. So instead of having 0.285, we want to have 1. So what we want is that the code converges to the solution where this last eigenvalue is equal to 1. So this state is fully occupied. So if you want to learn more about this, I mean the physics behind why do we want this to be occupied, you can check the paper written by Matteo and Stefano De Gironcoli, Physical Review B, 2005. The paper that introduces the linear response calculation of U. It's discussed in more detail, and maybe Matteo can comment later. But what I want to show you now, that is how to force the code to occupy this eigenvalue. I mean, to make it equal to 1. And why this eigenvalue? This is because this is the only eigenvalue which is non-degenerate. The others are degenerate, so we don't want to touch them. So we want to push it to 1. And how to do that? We have a keyword which is called starting NS eigenvalue. And it depends on 3 indices and equals to some value. So some value is the value which we want to enforce. So it's 1. Now, these 3 indices are what? The first, which is 5, is the index of the eigenvalue which we want to change. In this case, it's the 5th eigenvalue. If you count 1, 2, 3, 4, 5. So we want to change the 5th eigenvalue. Second index is spin. In this case, it's 2. So for the first atom, it's the second spin channel. So we say spin 2. And the last index is the atomic type. In this case, it's atom 1, which is iron 1, is the first atomic type. So we put 1. While for the second atom, we say the atomic type 2, first spin channel, because it's in spin 1. And again, it's the 5th eigenvalue. So we need to specify these 2 new keywords. And what it will do, it's basically from after the first iteration, the code will sort of try to converge to the solution where this eigenvalue is 1. Sort of hinting to the code, please try this path. So this is how it looks like in the SCF and NSCF input. We need to add these 2 keywords. And okay, I wanted to keep it as a surprise, but let's try to do that and see if this works. Okay, we close this. So let's save these files. So we copy everything there. And let's clean up this repository. Okay, we're good. Now let's modify the inputs. Go here. And now we add these keywords, starting NS eigenvalue. So it was the 5th eigenvalue, well, the second spin channel for the first atomic type. And the 5th eigenvalue for the first spin channel, the second atomic type. And this we need to copy also in the NSCF calculation. We save. We open the NSCF input. And we paste here. Okay. And we repeat those steps as usual. So first we run the SCF calculation. Okay. So let's wait. The SCF is pretty quick. Okay, so once this is finished, we can analyze the output file and see what the code does actually. So if the pseudopotential, there is a question in Slack. If the pseudopotential is produced with 2D manifolds and one is empty, how can I apply the U correction? So now in Quantum Espresso, sorry, before I answer, let me submit an NSCF calculation so we don't lose time. So now in Quantum Espresso, it is not allowed to apply the Hubbard U correction to empty states. So you can apply only to occupied states. Still, if you want to do it, there are ways how to do it. You can, from the input, there is a new keyword called Hubbard POC, and it's written like this, Hubbard POC. You can check the documentation. So basically, you can slightly cheat in the sense that you change the occupation from exactly 0 to 0.1. So the code will still allow to apply the Hubbard correction. So if you have two Hubbard channels and both of them are D, so you can act with the Hubbard U on both of them. You just need to say which manifold, like you write in the input. Let's say, let me show it here. Just a second. Yes, suppose we have iron 1, 3D, and then suppose we have again iron 1, but another D. Okay, doesn't make sense. But suppose we have 4D, I mean, it's empty, okay? So you can apply a different U value, but if it's fully empty, it will not work. So you will need to add here another keyword equals, let's say 0, 1. It's the occupancy of this manifold. So we need to say which atomic type. It's the first atomic type, and then the channel. Yeah. So we have two Hubbard channels. So the first one is 3D because it appears first, and we want to change the second one. So we need to put second channel. I don't remember in which order. It's first the atomic type and then the type channel, or vice versa. So we need to check the documentation. I don't remember. Probably it's the correct. Yeah. First atomic type, which is iron 1, and second channel. So just say occupancy 0.1, so the code will run. If not, it will not run because it's not allowed to apply the U correction to fully empty states. Okay, but just to wrap up this session, yeah, NSCF is finished. We run the PDOS calculation. No, input. Output. Okay, and we check the Fermi energy. I did some mistake, I guess. Yes, I forgot to put oxygen. It's not a big problem. So the Fermi energy is 1595. So we put here 1595. Okay. And now we run the script. And we open the DOS. And bingo, we open BandGap. Magic. So with this trick, we managed to open a BandGap. And the BandGap value is 2.76. Experimental one is 2.4. So you see we overestimate. It's not perfect. It's not too bad, I would say. If DFT gives you, I think, much worse band gap. I don't remember what is the value, but with DFT+U, we improve a lot with respect to DFT, but still we are not very accurate. So in cobalt oxide, it was great. Now it's less great. That's how it works. But the very important message, as I already said before, on the left, we see the standard DFT+U calculation and the total energy. And on the right, the DFT+U with the trick of starting an S eigenvalue. But if you compare the total energies, you will see that the one on the right is lower, which means it's really the global minimum. One on the left is higher, which means it's a local minimum. So as I said before, if you run standard DFT+U calculation, you get in the local minimum. With this trick, you help to the code to find the global minimum, and you open a gap. And then there is a new exercise about chromium oxide, and Matteo will discuss about it after the lunch break. But you will see what do you have in the case of chromium oxide. Is it as good as, is it as we are so lucky as in the case of cobalt oxide, or maybe we're less lucky like in iron oxide, or it's some other scenario, but you will see. Okay, any other questions so far before we stop or close this session? So, okay, actually Nicola is asking, can you still open the gap with the trick even without the +U? I think no. I haven't tried, but I think it will not work. So could you please tell us if there is any possibility to calculate Hans coupling with quantum espresso? So J, it's a long story. So in 2011, Matteo and coworkers published a paper where they compute J for copper oxide, and it really improved a lot the results. But it was a non-magnetic calculation. But if you try to compute for magnetic systems, it's difficult to converge the J parameter. Also, there are some issues with the functional, the DFT+U+J functional, which was derived. It's still an open question, and researchers are working on that. In particular, Edward Linscott, who is one of the lecturers and tutors, they put on arXiv a very new functional that sort of tries to address this issue. And by the way, also Edward and David O'Regan, they actually also have a somewhat different version of linear response that allows to compute the J parameter. But now, currently in Quantum Espresso, we don't have ready-to-use code to compute J. Okay, any other questions? Or maybe we can wrap up here before the exercise 3 after the lunch break.
Just one thing, someone asked this question that as the U parameter is the multi-minima problem, what can we do for complicated materials? Suppose for those materials that's the non-degenerate fractional occupation is not obvious.
Yeah, it's a very good question. I think one of my colleagues, Louis, should be here around, but he cannot talk. He can maybe answer on Slack, but they work on this problem. I just showed you the trick with starting an S eigenvalue, but what they do, they use DFT+U with constraints. Here it is. Maybe, Louis, do you want to take this question? He's there, but maybe not there. He went out. Okay, so basically, yeah, they use the constraints and they can explore really the potential energy surface. They find really plenty of local minima. And yeah, they sort of, with their method, they are able to find the lowest energy in magnetic configurations. So they should have a paper on archive soon, or maybe it's already on archive. So maybe you can check, Louis Ponnet and Nicola Marzari. But it's really, really interesting question. And yeah, people are working on that. Maybe after the lunch break, Louis can comment more about this. Okay, do the DFT+U calculations work well with the non-collinear calculations or with spin or decoupling? That's another excellent question. And there is another colleague, Luca Binci, who should be also around. I don't know if he's there or not. But he implemented the non-collinear version of DFT+U. Also, the HP code was extended to this case. So yes, it's possible. It's not yet public, but it should be public in the near future, maybe in one of the future releases of Quantum Express, including spin-or decoupling. They already applied it to some manganese-containing compounds, and it was really improving a lot the results. Okay, maybe the last question, and we stop here. How starting NS eigenvalues affect so largely the result, band gap? When should we include it? So, how does affect so largely the result? Well, because it simply allows us to converge to different minimum. I mean, without that trick, we get to the local minimum. With that trick, we get to the global minimum. And the difference is huge. Either it's metallic or insulating ground state. But what it does underneath is that if you open the STF output, and then you go to the first iteration, yes, iteration 1. So before iteration 1, the code somehow redistributes electrons on the 3D shell. But then, yeah, you see how it's redistributed. But then after the first iteration, since you ask the code to change the eigenvalues, there is this warning. Modifying starting NS matrices according to input values. So you see that here we have the fifth eigenvalue exactly 1, because we asked from the input, we asked it to be 1. You see also here. Okay. So for us, starting from this first iteration, the code is already sort of kicked in the different direction, and it tries to go that direction, and it manages to go to the global minimum. But if you don't do that trick, the code alone doesn't manage to get to the global minimum. So this is the eigenvalue that was changed. Yeah, you can simply open the output and check that it worked well, in the sense that the code did modify the eigenvalue. Okay, I don't want to take more of your time. I think we should close this session.